Hello everybody, this is Mr. Strager, back again with another Big Ideas lesson. Today we are going to be starting Unit 5. Now, to those of us students who just got out of Unit 4.3, if you're watching this, don't worry, this is not an error, this is correct. We are currently going to be skipping, for the 2022 school year, we are going to be skipping sections 4.4 through 4.7 just for right now. Overall, they don't have as much to do with lines as 5.1 does. So we've been talking a lot about how to find equations of lines in point-slope or slope-intercept form. However, today we are going to be talking about what happens when we have a system of linear equations. A system of linear equations is defined as a set of two or more linear equations. And the idea here is this. We're going to start looking at what happens when you have multiple graphs on this, or multiple lines, I should say, on the same graph. We're going to start to see the interactions between these lines. We're also going to be able to see if we can spot some unique solutions to these graphs. So you will absolutely need graph paper for the next few lessons. It is absolutely required. Here's what I'd like you to do. On your graph paper, I have some pre-generated graph paper here, I want you to graph out the following. I want you to make a line that starts at y equals 3 and goes up 3 over 2, up 3 over 2, or down 3 left 2, over and over and over again. What's going to happen is you'll end up with a line that looks something like, or maybe not something like, but exactly like this. There we go. This right now is not a system of linear equations since there's only one line on here. But let's fix that. We're going to put a second line on this graph that goes as such. It's going to start at 7 and go down 1, right 2 each time. So down 1, right 2, down 1, right 2, down 1, right 2, and the pattern continues on and on and on. This is now a system of equations since there are two lines on the same coordinate grid. As we look at these, we can start to see some solutions of these lines. As a reminder, a solution to a linear equation is what happens when you find a point that's on that line. So for instance, a solution of the red line would be 0, 3, or -2, 0, or 2, 6, or so on and so forth. A solution of the blue line would be anywhere there's a point, so somewhere like 4, 5. We'll be talking about how to test solutions in a second, but can I ask you something? Is there a location that is a solution for both the blue and red lines? In other words, is there a place where both the blue and red lines exist at the same time? There is only one place on our graph where this happens. Right here. If you look at this green dot, it's on the red line and it's on the blue line. So it is a solution of both the red and blue equations. This unique solution is the solution of a system of equations. The solution of a system of equations is what happens when you find a coordinate pair that fits on both lines. So, the solution of a system of linear equations is a coordinate pair, which we like to write as x, y, that is a solution for each linear equation. There's a name that you're going to hear me call this often or over and over again. I'm going to call this the intersection. Just like at a four-way intersection or a three-way intersection as you're driving, the intersection is where the lines cross. Our goal for 5.1, and in fact for 5.2 and 5.3 to some extent, is to actually find this intersection. So here's what I want us to do. Before we start talking about that, let's talk about solutions again. I want you to flip over to page 135 and take a look at problem number 1. The instructions for problem number 1 are as follows. We are given a point and two lines. So we're given a system of equations and a point. And we want to test out if this point is actually a solution to the whole system. To figure that out, we need to plug it in to both equations and see if we end up with something that is true. Let me give you an example. Let's look at this first equation, x plus y equals 4. If we plug in the point 3, 1, 3 is our x, so we're going to, instead of writing x, write 3. 1 is our y, so instead of writing y, we're going to write the number 1. And our goal is to figure out if this is a true statement. When we don't know if something is true, we put a question mark over the equal sign. Like we're questioning, does this equal 4? Well, most of us know that 3 plus 1 is 4, and 4 does equal 4. So we've tested out this point in our first equation and found that it works. So we get a check mark. That shows us that, hey, that one works. Let's try for the second equation, where it's going to be a little bit trickier. In the second equation, we have 2 times, instead of x, we're going to put the x-coordinate 3. Minus, instead of y, we're putting the y-coordinate 1. And again, we don't know if this does equal 4 or not, so we put a question, or sorry, 3. My apologies. We don't know if this equals 3 or not, so let's figure it out. What's 2 times 3? Well, 2 times 3 is 6. So we have 6 minus 1. We're trying to figure out if that equals 3. And what's 6 minus 1? 6 minus 1 is 5. 5 does not equal 3. So we give this one an x. The only time your point is going to be a solution to the system of equations is when it satisfies both equations. It satisfies the first one, but it does not work in the second one. What that means is, even though 3, 1 is a point on this first line, it is not a point on the second one. Therefore, it is not our intersection or our solution. We say 3, 1 is not a solution to the system. What I want you to do now is I want you to take a look at problem number 2. Try out number 2 on yourself. Pause the video here, and we'll come back to examine the answers. So again, pause the video, see how you do. How'd you do, y'all? As you see, the first equation does work with the points 1, 3, and the second equation works with the points 1, 3. Think about it like this. Since 1, 3 works for both lines, there's only one place it can be. It has to be where both lines exist. In other words, our intersection. So, because it's at the intersection, 1, 3 is the solution to the system of linear equations. Let's go down to number 9. So what we have here is this. Now they're giving us a graph. And from this graph, we need to figure out if this, or if we can find the solution of the system. Then we're going to check our work just to make triple sure that it actually is the solution to the system. Well, finding the solution is the easy part. The solution is where both lines exist. And there's only one place where both lines exist at the same time. It's right here, at the intersection. So our solution is where the intersection is, which is at 4, 2. So our solution should be 4, 2. But we don't know until we check it. So we take the point 4, 2, and we plug it into our equations. If we plug 4, 2 into the first equation, we get 4 plus 2 times 2 equals 8. 2 times 2 is 4. 4 plus 4 is 8, so yes, this one does work. Normally you'd show each step, but I'm sort of going along for expediency's sake. In the second equation, we have 3 times 4 minus 2 times 2, and we want to see if that equals 8. Well, 3 times 4 is 12. 2 times 2 is 4. So does 12 minus 4 equal 8? It does. So this just confirms that we got our point correct. That is the point 4, 2. At this point in time, I'd like you to flip over to the back side of your sheet. We're going to take a look at a different set of problems. Now, here's where your memory of units 3 and 4 are going to really come into play. Let's take a look at problem number 10. We want to solve the system of linear equations by graphing. So our goal is to graph both of these two lines, then figure out where they cross, if they do cross. The first problem, problem number 10, is in slope-intercept form, which makes it a little bit easy for us. Let's take a look at this first equation. To graph in slope-intercept form, the first thing you're going to do is put a dot at your y-intercept. The y-intercept is always this plus something number, so we put a dot at y equals 3, because that's the y-intercept. For our slope, we might need to edit this a little bit, because we don't have a fraction to find the rise and run of. Remember, if your x doesn't have a number in front of it, you can always put a 1. So this is really negative 1x. Well, hold on, that still doesn't tell us a slope. That doesn't tell us a rise divided by a run. That's just the number negative 1. Here's the trick that we should remember. Anytime you have a whole number that you want to turn into a fraction, you put it over 1. So our slope is negative 1 over 1, meaning we go down 1 and over 1 to find our next point. With that, we have 2 points, so we can make our line. Like so. There we go. All right, good enough. Let's try out the next one. Again, you're going to put a dot at the y-intercept of 5. And when you don't have a slope, you can put a 1. To turn this 1 into a fraction, we put it over 1. So we're going up 1 over 1. Up 1 over 1. There's our point. And we connected 2 points with a line. This graphing part should be review, and yet despite that, I actually think it's kind of the hardest part of this whole thing, is just remembering how to graph each type of form. You'll see what I mean in a second. Do we have a place where the lines cross? Do we have an intersection? We do right here. This solution is negative 1, 4. So that is the solution to our system of linear equations. Let's try a little bit of a different one. Let's go all the way to number 15. Number 15 is not in slope-intercept form. This is in standard form, which is something else we learned in Unit 3. As a reminder, when you have something in standard form, you're looking to solve for the x and y intercepts. Then you graph the intercepts and connect them with a line. To solve for our intercepts, we would normally cover up 1, solve the equation that's left over, and have our intercepts. But you may notice that in this equation, we don't end up with very nice numbers. Anytime you end up with numbers that don't work with the thumb method well, I am sorry, but it does mean you'll have to put these in slope-intercept form first before you can graph. I know, it's a little bit of a pain. I'd like you to pause the video here. Just write down the slope-intercept version of these lines, and then we'll take a second to graph them. Let's pause the video now. Welcome back, everybody. Did you get y equals 3/4 x minus 7/4 and y equals negative 5/2 x plus 3/2? These equations suck to graph. That's the one downside of solving by graphing, is sometimes the numbers just don't work out. But nonetheless, we can graph by estimating where they should go. So we plot the y-intercept of -7/4. Well, -8/4 is just -2. So this is really close to -2, but not quite there. It's 3/4 of the way to -2. As we graph this line, we go up 3/4, up 3/4. So we're going to keep doing that, keeping in mind that we won't end up on an exact point. There we go. That's sort of above the line, so it fits. We're going to draw a line through it, and again, it's an estimation. That's why we do the checks, where we plug in the numbers to the equations and see, because we won't end up with a perfect answer for some of these. We will in the next couple sections, though. So that's an estimation about where our line is. Next thing we need to do is graph the second one. So we graph 3/2, which is 1.5. We then go down 5/2. 1, 2, 3, 4, 5, 1, 2. Right there. And then we connect them up with a line. When you use a straight edge, your estimations will be more accurate. I'm estimating that my line, or my lines I should say, cross right here at -1, -1. But we don't know until we test it out. If you plug -1, -1 into this top equation, you get -3 plus, or sorry, I apologize, 1, -1. There we go. If you plug this in, you get 1 times 3 is 3. -1 times 4 is +4, so you get 7. 1 times 5 is 5. Plus 2 times -1, that's -2. 5 minus 2 is 3. So 1, -1 is our point. For this next one, you will absolutely need your graph paper. But before we jump to the graph paper, let's take a look. Problem number 16 reads as thus. We have a test. It's 20 questions, and it's worth 100 points. The test consists of X, true or false questions, worth 4 points each, and Y, multiple choice questions, worth 8 points each. How many of each type of question are on the test? We've done a lot of rough draft thinking, so I think now I'll introduce something that we might not have talked about as much in the past. We mentioned it, but I don't think we've ever discussed it. That's the table method of rough draft mathematics. When you don't know how to organize your information or where to put it, you can always make a table. Keep in mind, for this table here, we are talking about systems of equations. So we're going to want to make 2 equations from this problem. Apologize for the very unstraight lines. To make this table, here's what we're going to do. We got to ask ourselves, what 2 things are we trying to measure here? For instance, if we had a problem that was talking about, oh, I drove 50 miles across 3 hours, my 2 equations might be about miles and hours. If we were talking about selling coconuts, it would be 1 equation for coconuts, or number of coconuts, 1 equation for the price of coconuts. Here, the 2 things we're talking about are the number of points on a test and the big overall question, how many questions? So number of questions. In the far right, I want you to put the word total. This makes it much easier for us to put our totals. We know that anytime we have an equation, it should equal something. Do we know what our total number of questions will be? Yes, it says a test has 20 questions. So we put 20 in here. Do we know our total points? Also, yes, we know it's going to add up to 100. Very nice. In these other columns, we write down the 2 types of questions we have. True and false, and multiple choice. Let's take a look. What in our problem represents the number of true and false questions? This is tough, because we don't actually know how many true or false questions we have. Instead, we're given the variable x to represent the number of true and false questions. So, we write x in this box. It's an x box. What represents the number of multiple choice questions? Again, we have y multiple choice questions. So we put y in here. By the end, when you have an entire row filled out, all you need to do is figure out how to put these together. Since we know we're adding up the number of true and false questions plus the number of multiple choice questions, we write the equation x plus y equals 20. That's one of our two equations. But what do we do for this one? For the points? We have to ask ourselves, how many points are in the true and false category? You may be tempted to say 4 points, but is that all the true and false questions? No. 4 points represented 1 multiple choice question. Oh, sorry, 1 true or false question. How do we represent all of the true or false questions? Well, think about it like this. If we had 10 true and false questions, if we had 2 true and false questions, how many points would there be? Well, 2 times 4 is 8. If I had 10, how many would there be? Well, 4 points times 10 questions is 40. So what we're doing is we're multiplying the number of points times the number of questions we have. We already know what the number of true or false questions is represented as. It's x. So 4 times the number of true or false questions is 4x. What about the multiple choice questions? We know they're worth 8 points each, but how do we represent all of the true or the multiple choice points? Well, if each is worth 8 points, and we have y multiple choice questions, we represent it as 8y. Again, since we're totaling these up, all we need to do now is add them together. 4x plus 8y will equal our total of 100 points. Now is where we will need our graph paper. And here's what I would like us to do with it. I want us to make a graph similar to the one down here. However, I'm going to let you know, the graph that is in your student journal is not big enough. You need to make a graph that is at least, it's actually sort of hard to catch all on the screen, you need to make a graph that is at least 25 units in the x direction and 25 units in the y direction. So, let's do it. Take a second to pause the video and make a graph that is at least 25 units in the x direction and 25 units in the y direction. Hopefully you had a chance to make the graphs. Now we are going to figure out how to graph x plus y equals 20 and 4x plus 8y equals 100. Remember what form these are in. Both of these lines are in standard form. When we have something in standard form, we can use the thumb trick, or, if that fails, put it into slope-intercept form. According to our thumb trick, we can cover up the x to solve for y, and the y to solve for x. So here we have, well, y equals 20. That was easy. Y equals 20. If we cover up the y, we get x equals 20. So we already know how to graph our blue line here. We put a dot at x equals 20, a dot at y equals 20, because those are our intercepts. Then we connect them up with a ruler, like so. Right there. And we should get this very nice diagonal line. To solve the other one, we use the same trick, but keep in mind, you will end up with a decimal for one of your two answers here. Let's take a look. 4x plus 8y equals 100. If I cover up my y term, I just have 4x equals 100. So let's solve that. If 4x equals 100, what do I need to do to get x by itself? Well, we divide both sides by 4 and get x equals 25. Now you see why I wanted your graph to be at least 25 big. For the y variable, we cover up the x, and we have 8y equals 100. So 8y equals 100. We divide both sides by 8. We should end up with a decimal. We should get 12.5, or 12.5. So, again, we plot our points on the x and y axes. So we plot our y value of 12.5. We plot our x value of 25. And when we make our straight line, we should notice these lines cross. Not only do they cross at a very specific place. So I'm going to draw out my line like so. Just want to make sure I get it 100% correct. There we go. And that's our line. This is why it's important to use a straight edge, because there's no other way to accurately get a result from this. But notice that we have an intersection here. What are the coordinates of the intersection? I'll zoom in so you can see a little bit better. What are the coordinates of this intersection? Well, x is 15, y is 5, so this is 15, 5. We now have what we need to answer the question. Because our question, if you recall, is, how many questions of each type are there? And we already mentioned that x, anytime we see it, is the number of true or false questions. If our x here is 15, that means we have 15 true or false questions. And if our y variable is 5 in our solution, and y represents the number of multiple choice questions, it means we have 5 multiple choice. And there we go. Thank you so much, everybody. I will see you next time.